Okay, everybody, we've been talking about the electron cloud this week and how in our contemporary idea of atomic structure, the electron cloud gets studied and how it is modeled. And in our quantum view of the electron cloud, it is very dynamic. We have orbitals that are really just probabilities. We know that those orbitals are not static, that nearby atoms, things like electromagnetic light waves and other factors can change the electron behavior in those orbital zones. It's very complex, but we do have a basic model for how our electron cloud is configured. In other words, based on a variety of factors that electrons can be put into a particular zone that we call an orbital, and that orbital can have a particular energy, and also how those electrons have a certain type of angular momentum we call spin. We're not going way into the weeds like that. We're just sticking to this as a very high school level way of looking at the way electrons are configured in a particular element. And if we're looking at just a neutral elemental atom where we have the same number of protons and the same number of electrons, in other words, we're not looking at ions, positively charged cations, or negatively charged anions, we can model the electron cloud, and we have given there's a modeling system based on those principal quantum numbers we call energy levels, and those correspond essentially to the rows in the periodic table, starting at that top first energy level with hydrogen and helium, and the second energy level where we go from lithium to beryllium to boron, carbon, nitrogen, oxygen, fluorine, and neon. Then we move to the third row, and then the fourth row. And of course, we go all the way to 7, but we're going to keep this very simple in this little lesson here. We're not going to go way into the weeds. We are essentially modeling potentially any neutral element all the way up to krypton, which would be the last element on the fourth row, element 36. So we can pretty much model any neutral element from hydrogen to krypton just by modeling these first 4 energy levels. But we also have what we call sublevels, or we can call them blocks. And this explains why the periodic table is blocked up the way it is. We have those left 2 columns, and we call that the S block, and those correspond to these. And notice that the S block is 2 elements wide, in other words, or 2 electrons wide. And as we have been talking, an orbit can only have 1 or 2 electrons, a max of 2. And then off to the right, we have what's called the P block, and notice that in your periodic table, that's 6 squares wide. And so if we have 6 electrons and they can have up to 2 electrons in an orbit, we have 3 orbitals. In other words, 3 blanks here that can fit electrons. Remember, this is just all symbols. Just kind of accept it for what it is. Don't get lost in the weeds here. And then we sort of have this D block, and that is that transition, that corresponds to the transition metal zone of elements like gold and zinc and chromium and manganese. And notice that is 10 squares wide. And so 10 divided by 2 electrons per orbital, we could have up to 5 orbits. So I gave 5 blanks for those orbits. The F block, we never seem to talk about in General Chem 1, and that's okay. But that's 14 squares, that's 14 electrons, or 7 blanks, 7 possible orbits. We're not going to model that today. So, as we model the electron configuration of elements, I'm just going to walk through to start with plain old hydrogen. So hydrogen, as we know, is element 1. It has 1 proton and it has 1 electron. So its cloud is very simple. We just have an electron. And that electron is on the first energy level. That is the lowest possible energy. And that's because it's closest to the nucleus. So that electron doesn't exhibit as much independence, so to speak. So it's not as energetic. At least when we're talking about normal, not ionized, not excited by electromagnetic waves. And so we could say the electron configuration is 1s1. So we have hydrogen has 1 electron. It's on the first energy level. It has a more or less spherical modeled orbit, and we assign that an S. And there's just 1 of them, so it's not a filled orbital. And so what's this arrow? This is kind of the last piece of this puzzle. So the quantum energy, the total quantum energy of this electron has a spin, and this is totally arbitrary. Electrons are moving around in the universe fairly all over the place. There's no true up and down, but we kind of give it this up arrow. It's just, we start with an up. And so we say that it has an up spin, just except for what it is. Don't ask to go further. That's for way later down the road. And so that would be the electron configuration. And then this is what we call being of the arrow diagram. It's just another way of modeling the quantum states of the electrons in an element. Now if we move on to helium, which is element 2, we've of course have picked up an extra electron. And so we now have a filled orbital that have opposite spins. So we have this rule that tells us that no 2 electrons can have the exact same set of quantum states or quantum energies or quantum behavior. And so their spins, we model them as sort of being opposite or counterclockwise. Once again, this is very much a simplification. So if you have an orbit and that orbital is filled by 2 electrons, that means that we must put them as opposing spins. We have a positive half spin and a negative half spin. That's what you'll see in the textbooks. And we move on to lithium. We're on the second row, and we can start filling up our orbits, but only a certain way. And this is where we get into another itty-bitty picky rule. So lithium would give us a 3rd electron. Lithium is on the second row, second energy level. That element is found in the S block. So all 3 of its electrons are basically occupying more or less spherical kinds of orbital behaviors. Is it perfect? No, but that's just kind of roughly what they think it is. And we move to beryllium. That is also in that particular block. And so we have 1s2, 2s2, and notice that when we add up these superscripts, they add up to 4, and that is element 4. So basically, here's a little trick. Count up your superscripts when you're doing these electron configurations. If they add up to your elemental number, you might have done it right. And so as we move across the row, we move into that new block to the right. We call that the P block. So you need to be looking at your periodic table while we're talking about this for this to make sense. So if you haven't, go stop this video and go get it.